Welcome to EEE145, Chapter 5, Relay Input Devices, Part 2. All right, last class period, we looked at the current transformer. This time, we're going to look at voltage transformers. So it's we're going to parallel the same logic and just go down. First question is always asked is, we need ears and eyes in the power systems. So what important quantities do we need to measure for the health of the power systems? So one easy way to tell if your system is healthy, look at your voltage levels. If your voltage levels are nominal or very close to the expected number, you're fine. If your voltage is too high, you have some issue with generation. If your voltage is too low, most likely you have a fault in the system or you're overloading your system too much. So voltage is an easy way to tell if your system is healthy. What are nominal level voltages we typically see? Well, for distribution, typical levels are up to about 25 kV. Right. You might see a rare chance it might go above that. Transmission level, this is typically 69 kV and above. And above. Other typical number, for example, 115 kV, 230 kV. These are very common numbers you'll see in the power system, right? Lastly, major group is generation. So generation sites, they're typically a little bit lower. Again, this is up to about 30 kV. Okay, so those are the three major blocks you're going to see for voltage levels. You have industrial level voltage, that's kind of parallel with distribution level as well. Okay, what are some general safe voltages for humans to interact with? Again, just look at what your house is. 120 volts is the standard we use. This is household voltage. Okay, you might see some utilities do 115 volts. And it's almost 120, but they use 115 because if they're running 115 kV system on their transmission system, just going 1,000 to 1 ratio, you could go down to 115 volts. So it's just to make it easy, right? So 120, 115, some utilities we use them, but they're pretty close. All right, which device do we use to read the voltages in the power system from this high level voltage down to this 120 volt system? Well, we use something called a voltage transformer, right? This is an instrumentation transformer specifically for measuring voltage, right? Called a VT. This is the newer way we call this. This is also called a potential transformer. It's kind of the old way to say it, but a lot of engineers still call this. A lot of drawings will still have PT as well. Okay. But I think we're trying to get to voltage transformer more than potential, but you'll see PT or VT all over the place. Honestly, I'm trying to get used to calling it VT. I've called it a PT my entire life, so I might even mess up and call it the old thing. So that's the main thing we're gonna look at is this voltage transformer to go from this high voltage 25, 69, 30 kV down to 120 volts. Okay, now what do they look like in the real world? Well, here's some decent pictures to show you. So the right-hand side is a diagram of what it looks like. Left-hand side is the actual picture. Now I'm gonna try to show you what device is actually what, because it's kind of a little smushed up together. So you got your main line, and then a VT will typically, quote, hang off a line. So you tie it to the main line, but then it just draws out. So in this example, you have the main conductor, which is the bundles up here. We're gonna have a small little wire coming out. This is your wire to your VT. It's gonna go through this little coil, this insulator right here. So this is what the wire hanging off the main bus looks like. Okay. The main bus is this right here. This is the main power. This is where the main current is drawn through. So you can see this is the main line right here. Again, just try and color code you so you know what's what. So that's the main line. Okay. And then you'll have the actual VT itself, which is this point right here. That's inside this box, like so. So 3 boxes. You'll typically see 3 of these, 1, 2, 3 for A, B, and C phase. Okay. This is A phase, B phase, C phase. Okay. So that's how you'll see, that's typically what you'll see a VT in a distribution station. You'll see three boxes with insulators and a little wire connecting to the main bus or the main wire. Now, on high voltage transmission side, we'll typically use something called a CC, capacitive coupled, or I think they just call it capacitive voltage transformer. Okay. Capacitive voltage transformer. Some people might call it CCVT for capacitive coupled voltage transformer, but I'm pretty sure the correct terminology is CVT. Okay. So this is basically just capacitors there and a smaller voltage transformer. So if you look here, you're going to have your, oh, let's use the same color code as before. So yellow is the lead wire going to the actual potential transformer. So here, this part is that main small wire and all of this right here, this whole thing, okay? And then we have the main unit, which is this whole thing right here, okay? This is the voltage transformer. That's inside this box right here, okay? And then here is the main line coming in. You could kind of see it right there, okay? Now, this one's really big. Notice the person right there. This is for A phase only. There is a B and C phase. It's most likely to the left and right of this page, but they just only show you for one set, okay? So those are the 2 ones, just your standard VT and then your capacitive voltage transformer, okay? We're going to mainly concentrate on the top one, VT, for now, and we'll briefly talk about the CVT as well. All right, so let's keep on going. So remember, the whole point of this is to take high voltage and transform it into a lower voltage, so the meters can use it. We can interact with it if we need to attach a meter to it. So typically, you want lower voltage and lower voltage level, lower current levels, because then the actual meter itself can be made smaller and it'll be cheaper, right? We technically could make a meter directly to connect to a 115 kV system, but it's gonna be really, really, really expensive because of the insulation we need to build into the meter. It's much easier to use a PT to bring it to instrumentation level voltage and then just run a bunch of meters off of that. Okay, so what are the typical voltage we see in a power system? We kind of made a few, but let's get a little more exact numbers. 12.47 kV is one. Common ones are 13.8 kV, you'll see. You might see 14.7 kV, right? 21 kV. These are, you might even see some lower ones, but these are like typical voltage levels you'll see. And we kind of just chose these voltage levels over the course of like 100 years, and we're kind of just stuck with it, right? We all kind of agree to use these certain voltage ranges, so we're not having something just random out left field. Okay, 69 kV for the transmission side, 115 kV, 230 kV. These are the typical voltage levels you'll see in the transmission side, especially here in California. Okay, all this is cool, but remember, this all should go down to a lower voltage level, which is 120 volts. And this is kind of standardized, right? You might, when I say standard, I should probably write 120/115 volts, because 115 volts is a pretty standardized number too. Okay, so just like the CT, we have a VTR, voltage transformer ratio. How do we define that? That's your voltage on the primary side divided by your voltage on the secondary side. So this is your voltage between here and here. This is V primary. And your voltage across here and here, this is your V secondary. Okay. All right. And then just like before, we could kind of choose the ratio to meet our needs. Okay. So let's keep on going. And honestly, it's very similar to the CT. So if you understood how CTs work, how to get the turns ratio for that, it's a very similar process here. That you just look at the voltage, you know what your secondary voltage is gonna look like, 120 volts, 115. You know your primary because that's what you designed as substation, and you just find the CT ratio. Okay. Like CTs, VTs also have a burden limit as well because there's only so much loading you could put onto instrumentation transformer before it goes into saturations. But it's actually not a big deal for voltage transformers because during a fault, the voltage collapses. So remember, in a fault, current increases and more current will saturate a transformer, right? But during, heavy loaded current transformer. During a fault, the voltage goes down. When the voltage goes down, it's going to be less current flowing through a circuit. So we actually unload the voltage transformer during a fault. So ironically, the voltage transformer is the most loaded under normal conditions. And when a fault happens, we actually make it easier for the VT circuit. So in that case, anytime you have a fault, there's less current in the circuit, less current equals less power needed equals no saturation, right? So you'll almost never see a VT ever go into saturation in the power system. I can't think of a reason why, except for you have some DC voltage, which it shouldn't, right? So this is a burden calculations are there for VTs, but they're not nearly as important as the CT because there's no way you could really damage a VT through overloading it. Okay. Now, how can we calculate the burden in the circuit? Because you still should, right? It's the same as the CT way. Add up the burden in ohms or volt amperes. The only time the burden will really make a difference is if you overload it under normal conditions, right? So here you'll have, let's say, you know, right here, 75 volt amperes at 5 amps. Okay, so this is the max load that you expect a VT. So make sure that your lead wires, all your meters, you want to figure out your total volt ampere rating at 5 amps. Make sure it doesn't go past 75 amps for a Y rated VT. Okay. But during the fault conditions, you don't have to worry about it. It's only during standard loading conditions. Okay. So why don't we go ahead and let's do an example real quick, right? To show you how VTs work. Again, if you know CTs, VTs aren't that much different. So let's kind of take a 20-minute break to work in this problem, just to give you an idea. Remember, our line voltage is 12.47 kV, so that's between here and here. This is your V primary. Then your secondary voltage down here. This is your V secondary. Find your turns ratio for this. Calculate the ideal VTR that you need, right? And then with the same VTR, figure out the burden of the circuit, and then select the correct burden designation based on the chart from above. Okay, so same idea as the CT, except we're doing PT, the VT level. Find your ratio, figure out that burden, make sure you get the correct classification, and that's pretty much how you order a VT for a manufacturer. Okay, so we'll take that 20-minute break and we'll be back shortly to check your answers. So thank you. Okay, welcome back to EEE145, Chapter 5, Relay Input Devices, Part 2 on voltage transformers. So lastly, we talked about the VT here. We had an example, so now we're going to go ahead and kind of parse through the example. So here we have a line voltage, it was 12.47 kV primary, or secondary voltage is 115 volts. Our VT ratio is just primary over secondary, which is 12.47 over 115. Now, for most part, you could kind of leave it right here. This is what you're going to say to manufacturers. Manufacturers, right? 108.4 is the actual turns ratio if you divide it out, but most VTs are rated in this ratio where you just have your primary voltage on top of 115 or 120 in the bottom. Just makes it easier because we can recognize 13.8, 12.48. Memorizing 108.4 is kind of weird. Okay, so this particular case, tell my manufacturer, I'm looking 12.47 high side, 115 on the low side, so I need that ratio. Next thing you have to do is look at your burden calculations. So again, in fault analysis won't be a big deal, but just for standard loading, you got to make sure you're not overloading your transformer every day or your voltage transformer every day. So your burden, we look at your voltmeter. The voltmeter itself is 20 volt amperes, so that's a metering. All the wirings, both to and from the relay, is 40 volt amperes as well. So what's the burden in the circuit? We're assuming you're drawing 5 amps consistently. So it's 20 plus 40, which is 60 volt amperes, right? So now you have 60 volt amperes. You go look at the chart. The chart says a Y class rated VT is for 75 volt ampere limit. So we'd go ahead and use that. I think the next lowest one is 35 volt amperes, so we would not use that because 60 is much higher than 35. We'd be consistently overloading the VT and you'll get an error reading. I would not go above 75 because anything, higher class you go, the more expensive it's going to be. So we're in the business of saving money. So choose a right class for the right fit. So in the end of the day, talk to manufacturer, say 12.47 kV primary, 115 kV secondary. That's my VT ratio. My burden is 60 volt ampere. So go ahead and give me a Y class rated VT and they'll know exactly what you're talking about. Okay. One thing to note here is if you notice, we didn't talk anything about the multi-tap ratios of X1 to X5. Typically, voltage transformers do not have those taps like CTs do. The main reasoning why is VTs don't vary in voltages too much because their system only has maybe 5 different types of voltages, and it doesn't make sense to make a more expensive variable voltage transformer because our voltages aren't going to change too much, right? Low current for CTs do change drastically from 50 amps to several thousand amps. So we do need a lot of options for that. But if you ever look in the manufacturer's catalog, VTs only have a few options compared to CTs that could have like 50 or 60 options. So power system voltages typically don't stray away from our standardized 12.47, 14.8, 7, 13.8 kV systems. So we don't need more than like maybe 5 or 10 VTs manufactured types to satisfy the entire power industry. Okay. So we're not going to be talking about any multi-ratio tap VTs. Those typically aren't in the power system. Okay, so we talked about the inside and the calculation of the VT. Let's talk about three-phase connections because in the end of the day, we're running three-phase systems. We need to know how to connect this VTs to the power system. So here, the first one is what type of connection is on the left diagram. This is a Y-connected VT. You could tell because on the primary side, you have all the neutrals connected to the ground. This is your neutral, right? So this is a Y-connected. Now, I'm not going to claim that Y connections are dominant in the power systems for VTs. VTs actually have many different type of connections compared to a CT. So Y connected is a popular one, but you will see delta connected just as much, right? Another good alternative people use is something called an open delta, which is right here. Open delta. It's called open delta because if you notice, there's only 2 windings. So if we try to make a delta connections, we'll only have 2 windings. It'll look like this. So normally you have a 3rd winding right here, but that's missing because we didn't buy it. And in this particular case, between the 2 windings is B phase, top is A phase, and top is C phase. So you might think that something's wrong, but an open delta will work just as well as a full delta for just basic reading of voltages. So this is called an open delta connection, right? Open delta connected VT. Right now, there are some downsides to it. is if the system is unbalanced, you won't get a good reading. So you'll actually get an error reading if the system is unbalanced. So this is a cheap solution that only works on a balanced system. Okay. So if you have some level of unbalancedness, this won't be able to accurately read negative sequence or zero sequence. It'll only be able to read positive sequence, balanced voltages. So you might get some errors in your reading for your relay. But if you need to cheap out and only buy 2 VTs and you only care about what happens in balanced systems, you can do it and it can work. Okay. So kind of said what's the advantage and disadvantage of it. We kind of talked about it, cheap solution. It you only have to buy 2 VTs, but only works for a balanced system. So we get less information, right? You know, I'll go ahead and write no zero sequence or neutral voltages, right? Right. Readings. Right. I mean, I guess you could technically try to read it, but it's going to be really, really wrong. So I would not. Okay. So again, Y connected, Delta connected preferred, but if you see open Delta, don't freak out. That's a viable solution. It's just a cheaper version of it. And again, there's other ones. They're very more specialized, like a broken Delta and whatnot, but we don't have to go for that. If you see it one day in a while, then just go look it up in the textbook that we have, and it'll give you some basic information on that. So that's pretty much your standard VT. Now let's go ahead and talk about a capacitive voltage transformer. So CVT, or like I said, CCVT. So potential transformers are not that expensive for low voltage, but once you get to the 100 kV systems, the PT or the VT gets a lot more expensive, just the VT, because you have to build insulation for a 100 kV system. Remember, insulation for 100 kV is a lot. They're like, this whole thing is an insulation, right? You can see those jagged edges. This thing could be 5 feet tall. So that's a lot of material to build into a PT. It's just going to be too expensive. So they realized we can use capacitors to create a voltage division to lower voltage. Okay. So here we could literally take the voltage here, right? And this is your voltage primary to the VT, okay? So here you'll have your VT, okay? This is your relay on this side. You'll have a capacitor right here, and this is your V primary. Actually, no, I probably shouldn't take primary. That might be confusing, right? So this is your voltage to the VT itself. So the VT directly. And then you have another couple capacitors, usually multiple in series. And this is to the system, right? Level. System voltage. And then this is a voltage, let's draw a different color, across the capacitors, V cap. And then you could you could choose a capacitive values to create a voltage divider and lower the voltage. Okay, so capacitors, so what's the added benefit of using capacitors? We can create a voltage division to lower the voltage on the actual VT terminals. It makes it cheaper, right? So my like for example, I could use a standard VT from the distribution side for maybe 12.47 kV, and then I have a 100 kV system voltage. I could create a string of capacitors to do that voltage division to go from 100 kV down to 12.47 kV. Okay. Additionally, we use capacitors instead of inductors. So we use capacitors to also help improve the power factor. So remember, we typically use capacitors on the power system to improve the power factor. Well, I'm going to have to create a voltage division. I can only use inductors, capacitors, or resistors. I might as well use a capacitor so I get an added benefit of improved power factor. Okay, so it's kind of like double duty. I'm helping the VT make it cheaper, and I'm also correcting the power factor problem on a power system. So everybody likes capacitors on the system, so the more we add, the better we're going to get. So CVTs are very common. They're exclusively used on the high voltage systems, right? You very rarely, if I've ever seen a 115 kV regular VT, they're almost always going to be capacitive coupled VTs because it's cheaper and power factor improvement is an added bonus. Okay, so let's go ahead and summarize what we're talking about with VTs. One big thing is they're they're in parallel with the power system. Remember, CTs are in series. Any voltage measurements we say are typically in parallel with the power system. You should always fuse a VT circuit. You know, VTs do not run high current. So if you somehow get high current in the VT circuit, you're going to damage it very quickly. Additionally, you have something wrong in your circuit. Most likely there's a fault on the VT itself or in the relaying circuit. So we need a fuse to cut everything off so you don't damage the equipment there. Okay? This is opposite of a current transformer where you should never fuse a current transformer. Okay. The secondary circuit where you put all your meters, because we're measuring voltages should always be measured in parallel. So you need to parallel the meters. Do not put the meters in series like we do in the CT circuit. So VTs are always done in parallel. So 5 meters in parallel, and the parallel wires go back to the VT itself. Okay. Never short circuit a live secondary VT circuit. Okay, this is opposite of the CT. So every meter and every device you put in a secondary circuit of a VT has a very, very high impedance. You should treat VT like an actual source. So if you ever short a source, what's going to happen? You're going to have an incredibly high amount of current. You'll most likely damage it, hurt yourself, or blow something up. So just general thumb, you should never put shorting bars or shorting wires on a VT circuit. That's a big no-no. You can cause a lot of damage. Okay. They're designed to have up to 120 volts nominal voltage on the secondary circuit. They're also designed to have about 5 amps nominal current on the secondary circuit as well, standard household voltages and currents, right? You need to select the correct burden designation for your VT or CVT whenever you're thinking about loading the VT down under normal operations. And then don't forget, use CVTs for high voltage circuits where needed. Okay. Last here, I want to show you a 3-line diagram because again, you need to see these. You never know it's very common that when you do interviews, the engineers bring out these sheets. So the more you know about them, the better you can pass their questions and get a job. Okay. So here, can you pinpoint where all the CTs and VTs are? So the VT, let's do that first. Okay. The VT is right here, right? Now notice this thing says PT because this is an older drawing probably, but this is your voltage transformer. Notice how it hangs off of the main line, okay? Now let's look at the CTs here. So CTs, you see one group is set right here, right next to the voltage regulator. You see another set here and here on one side of the transformer and another one on the other side of the transformers. So you can see this transformer probably has these CTs as slip-on CTs to the transformer itself. Now this CT next to the voltage regulator, it might be a slip-on to the voltage regulator, or it might just be standalone. right? That we'd have to go and look to see that. Okay, but again, just it's good to note. Remember, CTs are in series with the line. PTs or VTs hang off the line in parallel to the system. Okay, so that's all I have for today. So I want to thank you for showing up, learning about the CTs and VTs. They're very, very important in the power system. You're going to be seeing them all the time. And we'll come back next week for the next chapter on power protection basics. So thank you for showing up, and we'll catch you next week. See you around.